Just wait a minute, and we will start our next session. Next talk will be delivered by Alexander Weiss from University of Hamburg. Talk is titled Intermittency Phenomena for Mass Distribution of Stochastic Flows with Interaction and is made under my supervision. Okay, Alexander, you can go.
Okay. Thank you very much for the invitation to this conference and also for the introduction. So as already mentioned, I will talk about intermittency phenomena for mass distributions of stochastic flows with interaction. 1 second, please. Okay. So first, I will begin introducing the notion of SDEs with interaction and what that actually means. And furthermore, deliver an existence result of such solutions or a good type of solutions for such SDEs. Then I will talk about densities of mass distributions, or like explain more what that is and how exactly it is studied. And then in the end, I will talk a little bit about intermittency phenomena and try to explain what that is. So the notion of SDEs with interaction was, to my knowledge, introduced by Professor Dorogovtsev. And one version of this is like this here. So let A be a function of from R times M times R plus, where M is the space of probability measures on R, mapping to R, and B be the map from R times R plus to R, and let mu naught be a probability measure on R. Then the following Cauchy problem of SDEs is called stochastic differential equation with interaction for initial measure mu naught, or in a short version, just SDE with interaction. So when we look at this SDE with interaction, it looks astonishingly similar to normal SDEs, but we have a little added term here, or another dependence. We also allow the coefficients to depend on the mass distribution of the flow. Maybe I will draw a picture to explain that a little bit better. Can I draw now? Yes. Okay, so consider this. And we say that we start with the flow of some particles on the real line somewhere here. Like this is T, and this is the space R. And our flow goes and changes with the time. And so does its mass distribution, or moreover, how it is distributed along the real line. And exactly this dependence is modeled by the last term. 1 second. This might go here somewhere, or go even here. And this dependence on or this mass distribution is exactly modeled by the last term. So as you can see, mu t is defined to be the push forward measure of the flow with respect to u. And mu naught is if you look from the particle point of view, is the initial mass distribution of the particles in the space. So how the mass is distributed. We assume it to be a probability measure because we assume it to be a finite measure, and without loss of generality, we can just say that it's a probability measure by just normalizing it. Okay, why can't I? Okay, so in order to obtain solutions for such problems, we need a Lipschitz condition, just like for regular ordinary differential equations or stochastic differential equations. And for this matter, I propose the definition of the Wasserstein distance. For this case, let M be the space of probability measures, and mu nu be some probability measures of the space, and C mu nu be the set of all probability measures on the Cartesian product R times R, such that their marginal distributions are equal to mu and nu. Then the following distance, called gamma of mu nu, defined as the infimum of this integral, is called the Wasserstein distance. And the entire space M, gamma is called the Wasserstein space. And it's actually, in the case of R, a complete and separable metric space. And gamma is, a valid metric on the space. So coming further to the strong solution for such Sdes with interaction. This theorem was also introduced by Dorogovtsev and can be read in his book, Measure Value Processes and Stochastic Flows, with a good proof. And the statement is like this. There exists a unique solution on 0 to infinity to problem 1 I stated earlier, such that if the following conditions are satisfied. And the conditions are that A and B must be continuous. And furthermore, there exists a constant C greater than 0, such that this Lipschitz condition, which is essentially a Lipschitz condition on the, holds for all U and V in R, mu and nu in the Wasserstein space, or the space of probability measures, and for all T greater or equal than 0. This solution is also product measurable on this sigma field, where Ft is just the normal Wiener filtration. And it is measurable on intervals from 0 to T for all T greater or equal than 0. So the proof of this is basically kind of similar. You start with an initial measure as the measure value process, and then you reiterate it with a Picard-Lindelöf type of iteration, but I won't go into any more details here. So after introducing the notion of Sdes with interaction, one can see that the problem 1, there is a product which is mu t, the measure valued process. And it's actually, it models the mass distribution of the flow with time. And in our studies, we considered SDE problems with initial measures mu naught, such that they are absolutely continuous with respect to the Lebesgue measure. And we denote the density by P naught. So we will, in the remainder of the talk, only talk about this subclass of SDEs with interaction and study them. So when one looks at these kind of problems, some natural questions occur. So the first very important question, under which conditions, or if at all, do we have the property that also the mu t are absolutely continuous with respect to the Lebesgue measure? Then moreover, if we find some conditions such that hold, so what properties the pt have, and in particular, how is the behavior for t to infinity? So we will then just use the generated densities pt in order to investigate the mass distribution of the flow and no longer look at the whole measure. So before starting with the proof for the existence of such densities for mu t, I will just try to emphasize the idea of the proof. So if we write out for an arbitrary t greater than 0, greater or equal than 0, and arbitrary Borel set A, then mu t of A looks by definition like this, as mu naught of the preimage under U of A, since we assume mu naught to be absolutely continuous with respect to the Lebesgue measure, this is the same as the integral over this set with integrating the function p naught x dx. So if one looks at this term, it is fairly reasonable to want to apply the change of variables formula, so we don't have this thing here anymore, rather just the set A, so we have a well-defined Lebesgue density. And actually, yeah, and then we end up with this term after if we assume that we can apply the change of variables formula. So what can we conclude from this? So first of all, we have to prove that the diffeomorphism property holds for xut, or there exists a version such that it is a diffeomorphism. And we have to also ensure that the determinant of the differential is not equal to 0, since we have, for all u and r. And the next theorem will exactly provide us with suitable conditions in order to obtain this. So let A and B suffice the conditions of the existence theorem and assume furthermore the following. A is twice continuously differentiable with respect to u, and B is a function of this type, which means that it is 3 times continuously differentiable with respect to u, and 1 time continuously differentiable with respect to t. Furthermore, assume that A and B and its respective derivatives are all bounded. And then as the last condition, we assume that the derivatives also suffice the, the Lipschitz condition for some c greater than 0. And all uv and mu nu t greater equal than 0. Then mu t is absolutely continuous with respect to lambda, almost surely for all t greater than 0. So the first step consists of showing that xut is actually a diffeomorphism. And in order to, first of all, I'm discussing the ideas of the proof. And in order to show this, we will just apply the theory of stochastic flows, which was introduced by Kunita in his book, which I will later show. For this matter, we defined a semi-martingale like this, which is obviously a semi-martingale since this is bounded variation and this is just a martingale. Then the characteristics are, first of all, A u mu s, since we can represent the bounded variation part like this. And due to the representation of the covariation process, which looks like this, the characteristic G of UVT is equal to BUT times BVT. And now to apply the theorem, we need to compute the following norms. This is a little bit, this is a lot of text on the slides, I guess, but it is actually not that complicated. So we consider an arbitrary t greater or equal than 0, define our AU mu s to be a function FUS. And then we get for all s in 0 to t, the following estimate for this norm right here, which essentially follows from the boundedness of the derivative and the derivative and the initial function a. Then for the second norm, we also have a bound which is independent of s, but this time it is induced due to the Lipschitz property of AU mu s, which we also assumed beforehand. And then looking at these two norms, these are kind of similar with the same reasoning, basically why they are bounded by a constant independent of s. After computing this, we can conclude that these norms, if you look at this as a function that maps s to this norm, is actually in L1 from 0 to t, since they are both bounded by a constant, and this is a set of finite measure. And same goes for this one. then we can apply the theorem 4.65 by Kunita and get that there exists a version which makes XUT actually a diffeomorphism. So the first step is thus finished. It only remains to show that the determinant is non-zero almost surely for all ut r times r plus. And for this matter, consider such functions hn of s dot, which are equal to the derivative of a linear approximation of the Brownian motion. Here in this case, ti and ti minus 1 are just some what do you call it again? Some elements of a mesh, which has elements of 0 to t, and when n goes to infinity, the mesh shrinks and the distance of the elements goes to 0. So this is just, a basic construction, and one can choose one mesh of his wish, for example, dyadic decomposition or something like that. So after introducing this, consider the following ordinary differential equations. dxn ut is equal to a tilde. I will, on the next slide, specify what a tilde is. xn ut mu t t dt, and this part here. So our plan is to approximate our process with differential equations like this. Why do we want to do that? Because for ordinary differential equations, we have the Liouville formula or Liouville-Ostrogradski formula, which gives us an actual representation of the determinant of the differential of such differential equation. And it has such an exponential form. So yeah, the determinant is just this by the Liouville-Ostrogradski formula. Then if one just checks in the book of Bismuth, one can check that even for the coefficients I proposed, the differentials converge uniformly in probability to the differentials of our initial process. Yeah, uniformly on all compacts 0 to t, but well, this is a mistake. There should be compacts 0t and compacts from the spatial space. So it converges uniformly in probability, and thus we can just apply the limits on the left-hand side and on the right-hand side of these, and we see that the determinant of the differential is equal to the exponential function of this guy, since xn us also converges to xus, and this guy, which is basically the Stratonovich integral. Yeah, the circle means that this is the Stratonovich integral and no longer the Ito integral. Where a tilde was defined as this normalization drift, which you get when you switch from Stratonovich integrals to Ito integrals and vice versa. Yes, and since we have such a representation, we can finally tell that the determinant is non-zero for all u and t, almost surely. Oh, oops. So now I will begin with the main topic of this talk. It's the intermittency phenomenon for such stochastic flows. So we will starting an example, and as the example we take ordinary differential equations of this type here, where our coefficient function is equal to the integral of v minus u of the integral mu dv, but only for measures mu which have an existing first moment, obviously, otherwise this is not well defined. Now it can easily be obtained that the solution for the solution of the SDE with interaction, or in this case ODE with interaction, is given by this yeah, is given by this, where m denotes the mean of mu naught. So as you can already see, if we go further in time, or let t grow to infinity, then this process goes to m, or like every particle goes to m. So yeah, we can already denote that no matter where the particle starts, it will be attracted by the point m, which is the mean. And from this, we have the following occurrence. Oh, oops, sorry. The following occurrence. So if n is greater than r, then the greater moments, the ratio of greater moments divided by smaller moments converge to infinity as t goes to infinity. And exactly this follows from intermittency phenomena. Maybe I will explain a little bit more by painting a picture. So let's assume if pt would be some constant function p0 for all t, then this ratio would obviously not go to infinity. But what we have in our case is that pt is of this form for t to infinity. So first it is maybe like this. I'm sorry for these inconveniences. Then it goes more like this. And it is always more with increasing t attracted by the point which is m. So the mass distribution concentrates towards this point m, and it actually explodes there, which causes these, well, it happens only around the point m, but this phenomenon of the growing quantity reaching such high values is so strong that it actually influences its integral characteristics, which is basically what I wrote here. So it influences the ratio so strong that it goes to infinity. Okay. Good. And yeah. So here we actually see that these properties which are proposed are actually true. So in the example of 3, pt converges to the Dirac measure in M in the space of tempered distributions. So all mass concentrates towards this attracting point M. And if P0 is even a Schwarz function, then we even get the convergence, pointwise convergence to this function, where infinity times 0 is just defined as 0. Yeah. And this is so far everything I have or we have studied. There are many remaining questions, obviously, so because this was just like an introduction. So first of all, one needs to find out what the connection between the coefficients and the intermittency phenomenon is. Yeah, and furthermore, it is also interesting to study the multidimensional case and maybe even study more interesting functionals, like not only one Wiener process, but rather SDEs of this form. I will just omit the drift part. BK XUT mu TT dBKT, where BK are just independent Brownian motions. And furthermore, which I already indicated here, there's another problem to solve. So we can just add a dependence on the mass distribution, also on the noise part, which I had to erase, unfortunately, in the very last second. Okay, then thank you for your attention. Why can't I? Oh, yeah. I can't. Okay, yeah. Here are my references. And thank you for your attention. Are there any questions or comments?
At least, thank you very much. Maybe some questions there. Okay.
I would like to make one comment.
Yeah.
Look at the book of Boulot and Hirsch about Markov processes, and I don't remember the name of the book, but the authors are
Sorry, Blow and Hirsch?
Hirsch, yes.
And the first one was what? Okay.
Boulot.
Bull.
You. It's written like Hirsch, Boulot.
Okay.
The second one is Hirsch. It seems to me that they proved absolute continuity of mu t of the image measure, even if coefficients are Lipschitz continuous in a space. Not C2 or C3 like in your case.
Yeah. By the way, the C2 and C3 property was for the theorems that give the approximation of. Oh, okay, yeah.
Because when you study Kunita theory, you have to study maybe 1 plus epsilon or sometimes 2 plus epsilon to apply Kolmogorov continuity criterion for functions or for derivatives. In the book Boulot and Hirsch, they study some Sobolev classes. They proved that the flow is differentiable in U in the sense of Sobolev.
Okay.
And that Sobolev derivative satisfies a linear equation if you just formally differentiate with respect to U, your equation. They did not consider equations with interaction, but it seems to me that their approach works. I don't remember. Maybe the coefficients also depends on omega. Like
yeah, that would be necessary.
U, T, omega. I don't remember. So look at this book and maybe you can enlarge. So you can study more general case.
Okay. Yeah, thank you very much. I appreciate comments on sources very much because I struggle to find sometimes.
It's by the way, it is a very good mood for a master student. You have to struggle with something, yeah.
Yeah, that's true.
Okay, and let me do some comment also. I have to say that the aim of this work, I hope we will continue it, is to find the cases where the equation is organized in such a way that we will have some phenomena of partial mass concentration, which leads to intermittency for densities. So for us, it was good to get the density and to study its properties. And actually, I think that we will continue this work and apply some other statements for equation with interaction when we have shift compactness and we have no fixed center of stability, like in the example which Alexander presented, but the center of stability, if I can say roughly, is floating around the space, but mass still concentrated near it, and so we will still have intermittency. This is our aim in the future. Thank you.
Okay.
Okay, if there are no other comments, then we can switch to other talk.
Thank you very much.
Thank you. And I think that the next speaker will be Marie Bormann. Yes, with the talk devoted to some integro-differential equations. Yes.
Yes, thank you. I will share my slides. Okay, so I hope you can see this now. Okay.
Yes.
So then again, thank you again for giving all of us the opportunity to give our talks today. Maybe I should introduce myself again. My name is Marie Bormann. I have studied mathematics in finance and industry at Technical University Braunschweig in Germany. And I would like to talk about Feynman-Kac's formula for a specific class of Integro-Differential equations today. This was the topic of my master's thesis, which I wrote under the supervision of Yana Kinderknecht. And it is actually based on a paper of Yana Kinderknecht together with Christian Bender. And also I should mention that this talk that I will give, in a way, it is a continuation of two previous talks that Yana Kinderknecht already gave in this seminar. Okay. So as for a short teaser, so to speak, the equations that we are going to look at are of this kind here, where K is some appropriate integral kernel, and I'm going to tell you what I mean with appropriate later on. This operator L here is the infinitesimal generator of either a Levy process or a Markov process, or just generally some strongly continuous semigroup. So we do have different degrees of generality here, so to speak. And then V is some appropriate potential. And we are going to try and find a stochastic representation for a solution of this equation. Namely, we will see that in these two cases here, we will have a solution of the form expectation of some function of these processes here. Also, I should say that I only look at a solution, so I'm not discussing uniqueness of solution here at all. Since I do not know how much maybe my fellow students also know about Feynman-Kac's formula, I'm going to give a very short and general motivation. And then first of all, we are going to look at a case where in this equation, L is the infinitesimal generator of a Levy process. And then later on, the more general cases where L is the generator of a Markov process, or just generally some strongly continuous semigroup. And then maybe we are going to look at a few examples after that. So as for motivation, you probably all know that Feynman-Kac's formula connect stochastic processes and deterministic differential equations or Integro-Differential equations by representing solutions of such equations in terms of some appropriate stochastic process. And actually, via this connection, one can also then use numeric approaches from the respective other field. My background personally is a bit in finance. So for example, I can tell you that if you look at finance, at option pricing, there are some known and used Feynman-Kac's formula. If you look at Black-Scholes models or exponential Levy models, what is maybe more interesting is a recent trend maybe, namely it has become more popular in the last years to model processes from natural science, for example, using fractional calculus. So namely using derivatives and integrals of non-natural order. An advantage of that is that if you look at such a derivative of some non-natural order, then it is not a local operator anymore, but a non-local operator now. And then if you have, for example, a derivative with respect to time, you can now also take into consideration what happened some time before the actual time that you are considering. So one could say that you could model processes with memory now. This is relevant in many different disciplines. physics, chemistry, biology, also economics again. And also this sort of modeling approach leads to different kind of or specific kind of Integro-Differential equations. And for these, Feynman-Kac's formula are maybe less well known, which is why it makes sense to look at them. As for a simple example, maybe one could just consider the heat equation and then turn that into a fractional version of the heat equation. And basically then you already get an example for this kind of equations that I showed to you right at the beginning. But also specifically when it comes to this aspect that I just talked about, there was much more said about this in one of the previous talks from Yana Kinderknecht. Okay, now, as I said, first we're going to look at the case where our operator L is the generator of a Levy process, and everything in this chapter, so to speak, is based on this paper that I already mentioned. It's called Stochastic Solutions of Generalized Time Fractional Evolution Equations by Yana Kinderknecht and Christian Bender. And actually what was considered here is this kind of equations where, as I already said, L is the generator of a d-dimensional Levy process with a symbol psi now, so you can write it as this pseudo-differential operator. I'm using such an appropriate psi here. Then it is assumed that the initial condition U0 is from the Schwarz space, and then this integral kernel, I said before, it is supposed to be an appropriate integral kernel, and here's what appropriate means in this case. So it is a real valued Borel measurable function such that this condition here is fulfilled. And maybe as for an interpretation of that, we want k as a function of this second argument here to be in L1 plus epsilon for some positive epsilon. So in this way, k as a function of the second argument is supposed to be good enough. And then k as a function of the first argument, if this argument t tends to 0, then the function k may go to infinity, may explode, as long as we can control that explosion by such a positive power of t here. Okay, so that's what is meant with appropriate kernel here. And then the paper is called Stochastic Solutions, so I should tell you what stochastic solutions means here. Namely, if we consider again the same equation and we have some probability space and some RD valued stochastic process on it that almost surely starts in 0, then we call this process a stochastic solution to our equation if for any initial condition from the Schwarz space we can define this function u here just as the expectation of u0 applied to x plus our stochastic process, and if then this function u is actually a solution to our equation. So that's what is meant with the stochastic solution here. And now I will tell you about some of the results from this paper, only some of them. There are many more statements in that paper actually, but what one can see is that if we, well, let's say this differently, we define a function phi called based on that integral kernel k, namely phi t is a function on the complex numbers, and it is defined via this series representation here with coefficients which are defined recursively and which are defined based on this integral kernel k here. This is a well-defined function, and it is also an entire function. And we are going to see that this function phi will actually play quite a central role. Namely, if we look at this first statement here, it was shown in the paper that a stochastic solution to our equation exists if and only if the composition of phi and psi, where psi was the symbol of our Levy process, if this composition is positive definite for all non-negative t. And then in this case, a stochastic process xt provides an actual stochastic solution to our equation if and only if the characteristic function of xt is given in this form here as this composition of phi and psi. And here maybe if we look at the equation again, this equation features k and l, and now on a heuristic level, maybe this result here is not so surprising because it actually tells us that the characteristic function of xt is in a form given via this phi, which reflects the influence of the kernel k, since it is defined based on k, and then psi, which reflects the influence of that Levy process. Okay, so that was the first statement. And then secondly, if we also have that our function phi as a function of minus the second argument is a completely monotone function for all non-negative t, then we can have stochastic solutions with a specific structure, namely this structure here, where y is a Levy process with a characteristic exponent psi. And then these AT here, they are a family of non-negative random variables such that the distribution of the random variable AT has as its Laplace transform exactly this phi of t here. And we need y and a to be stochastically independent. So again, if phi is completely monotone, then our stochastic solutions can look like this. So a Levy process with this sort of time change here. And now this is everything that I'm going to tell you from that paper, because this second statement here is mainly what we would like to generalize now for the case where we don't have an operator L that is generated by a Levy process, but by a Markov process. And now,
Marie, excuse me, can I ask you something about this variables a, t? You just said that these variables a, t are non-negative random variables such that Laplace transform has the following form, but you don't say anything about the connection under different t. But after this, maybe when you organize the process YAT, do you need some connections for different t, or just for fixed t you have the expectations? That's all.
okay, so first of all,
do you need some relationship between these variables AT or not?
no, I don't think I need any of that. Actually, we only need sort of each AT on its own.
Distribution, yeah?
Yes.
Just distribution. Okay, so one can say that for every t, AT must be independent, taken independently from YT, from the process YT, yeah? Because
Yes,
you just use it under fixed t. AT you use under fixed t. This is my point. You don't need this stochastic independence as a processes. You don't have even the process AT. Yes.
Okay, yes.
Yeah. Under fixed t, you have such random variable which is independent from y, has such Laplace transform. Then this YAT gives us a solution. Yeah.
Okay, yes.
Mm-hmm. Thank you.
Okay, then let me go over to the next part where we will consider a more general setting. And for this, I might have to tell you about a certain tool that we are going to use, namely the so-called Hilly-Phillips functional calculus, which some of you might not know. So let me explain to you. As you generally do know, functional calculus is about formalizing the notion of inserting some operator into some function that is usually defined on a different domain. And here we are going to look at some strongly continuous semigroup, which is uniformly bounded on some Banach space X, which has an infinitesimal generator L. And then we're going to look at a certain class of functions. It is called ls of C plus here. And those are supposed to be functions that can be represented as Laplace transform of some complex measure mu on the non-negative real numbers. And now I will explain to you what I mean if I insert such an operator minus L into a function from this class here. And for that, I define this function phi t here from this class of functions into the Banach space of bounded linear operators on X. And for some function f, which is Laplace transform of some appropriate measure mu, phi t of f is just defined in this way. So integral over t, and then here we've got mu dt, where the mu is exactly the one from the representation of f. And then phi t of f applied to some element x from our Banach space is just defined like this, integral over t applied to x. And then again, using this mu here. And with this, I've actually defined just a function which is well defined and everything. And now instead of writing phi t of f, we will write f of minus L. And thereby, I have then explained to you what I mean if I insert such an operator minus L into such a function f from this class of functions. And we are going to use this functional calculus later on. Actually, we don't need uniform boundedness. One can trace the more general case back to this first case here. Okay, and as I said, we are now going to look at the more general case. Namely, we are considering a strongly continuous semigroup TT on some Banach space X with a generator L. We take some non-negative omega as small as possible, such that the rescaled version of our semigroup is bounded. And then, as before, we take a kernel which fulfills the same conditions as before. And as before, we also define this function phi. And then again, as before, we assume that our function phi as a function of minus the second argument here is a completely monotone function for all non-negative t. And thereby, by Bernstein's theorem, there are then random variables, non-negative ones, on some probability space such that their distribution has as a Laplace transform exactly this function phi. So one can then argue that this equation here holds for all complex lambda with a non-negative real part. And what we do need is a bit more than that, actually. Namely, we need this right-hand side here to exist for all lambda with a real part that is less or equal to omega, which we just chose earlier on. And then we also have this equation for such lambda. This is kind of a strict assumption, but we do actually need it. And then one last thing, we need to sort of reference measure mu on the non-negative real numbers such that our distributions PAT actually have a density with respect to that mu. Okay, so this is the setting that we need. And then we are going to look at this more general version of the previous equation, where now, as I said, L is just the generator of some strongly continuous semigroup. And also now we just have an equality in terms of two elements from our Banach space X. And now if our initial condition U0 is from the domain of that operator L, then we can actually write down a solution to this equation, which looks like this here. And this has to be interpreted in this in the sense of this Hilly-Phillips functional calculus. So we had our function phi before, then we inserted the operator minus L into it, and then we have some bounded linear operator on X, and then we apply that to U0. And this actually then gives us a solution to this equation here. And actually, in the following, we are going to see special cases for, well, yes, more specific semigroups and more specific Banach spaces. This is also the most general case. Actually, everything that is about Markov processes, so the setting with Markov processes will only be a corollary from this theorem here. And if we look at the proof, maybe very briefly, again, this proof is also based on the mentioned paper. Namely, in the paper, it is shown that this function phi fulfills a certain integral equation, this one here. And then I will only tell you about the idea of the proof rather briefly. So we rewrite this equation a bit, and then we also want to transfer it in terms of Hilly-Phillips functional calculus. So again, we want to insert our operator L in here, minus L actually. And well, we have to make sure that everything is well defined and so on. And actually then if we do that, we arrive at this equation 6 here, which features the Yosida approximation L, also its resolvent. And then basically we just need to take the limit, and then we see that the statement that I made earlier on is actually true. Okay, so this was the most general setting. Now we are going to look at the case where our operator L is actually the generator of a Markov process. So a bit more in detail, we consider some Markov process Xi with the state space Q, and X with the supremum norm is now supposed to be a Banach space of functions on Q. And we want that if we look at this semigroup, which is just defined in the standard way based on our Markov process, we want this to not only be a semigroup, but a strongly continuous semigroup, such that we actually have some infinitesimal generator L. And then we take these random variables AT, again, each of them independent from our Markov process, and such that AT has as its Laplace transform exactly phi of t. And also we again assume our kernel to be good enough and so on. And then we can look at this evolution equation here, where now, as I just said, L is the generator of a Markov process. And then we can write down a solution in a stochastic representation in this form here. So just the expectation of our initial condition applied to Xi. And then here we've got these random variables AT. Actually, since this whole setting is only a special case of the setting for the previous theorem, now the proof is very easy and very short. So from the previous theorem, we know that this here is a solution to our equation, and now we just have to look at, well, the specific structure of phi in this setting here, and then basically just use Fubini's theorem once. Okay, what we see is that this statement here is actually quite a direct generalization of the second statement from the paper that I mentioned. So previously L was the generator of a Levy process, now it's the generator of a Markov process. And then we've got this stochastic representation for a solution, and it actually has, again, the same structure as for the case with the Levy processes. Also, what we can see is if we look at this stochastic process here, then we actually only need the one-dimensional marginal distributions of that. So we could take any other stochastic process with the same one-dimensional marginal distributions for this stochastic representation. Okay, and then I also promised to include some potential here in the equation. What we generally need is a bounded potential, and then we need L plus V. V is the potential. We need L plus V to still be the generator of a strongly continuous semigroup, and we need a stochastic representation of that. So maybe in more detail, we take again our Markov process with the state space Q. We take a Banach space of functions on Q, and we choose, or we assume that we have such a function V, which we need to be bounded here. And we want that L plus V still generates a strongly continuous semigroup on X with such a stochastic representation here. And then, as before, we take our random variables AT, and then if we look at our equation, which now features a potential, we can write down a stochastic representation, or actually a Feynman-Kac formula for a solution, which looks like this here. And now we have this exponential term here, which is new due to the potential V. And actually what I said about the one-dimensional marginal distributions that are the only thing that is relevant, this is not quite true anymore now, because actually, in a way, we still only need one-dimensional marginal distribution of AT. Or if we look at it still as a process, we only need the one-dimensional marginal distributions, but we need more of the Markov process in a way. Okay, maybe we can look at one interesting special case. So if we have exactly the same setting as before, only we assume now that our kernel K is a bit more special, so to speak. Namely, we assume that it is homogeneous in this way here. So we want to have some beta between 0 and 1, such that if we look at K of T and T times S, then we want to be able to pull the T out in this way here. Okay, and well, stated briefly, actually, if K is special in this way, then phi, which was defined based on K, will also be special, and then those random variables AT will also be special and have a special structure. Namely, if we just define phi exactly in the same way as before, then we now only have to look at phi of 1 as a function of minus the second argument. Previously, we needed phi of t here for all non-negative t. Now we only look at it with t equal to 1, and we want this to be a completely monotone function. And then again, we have one non-negative random variable a with an appropriate Laplace transform. And then we see that our evolution equation is solved by this solution here, where, well, nearly everything looks as before, only these random variables AT have a specific structure now. Namely, before we had just appropriate random variables AT here, and now we see that actually all of them have the same random part A, and then they have some time-dependent part T to the power of beta. Okay, so this is maybe just an interesting special case. So if K is homogeneous, then so is phi, and then we have the specific structure of those random variables AT. Okay, and then maybe just to show you an example, and actually also the easiest possible example, probably let's look at the heat equation. So if we just, as a process, take now a d-dimensional Brownian motion, and we just take a rather boring bounded and continuous potential, then if we define operators TT like this, then we have actually a strongly continuous semigroup on the space of continuous function which vanish at infinity. And as an infinitesimal generator, we then have 1/2 Laplacian plus V. And what is known for a long time is if we just look at the basic heat equation, then we have such a solution here. And what we can do now using those previous statements is we can include some kernel, some non-constant kernel here in the equation, and then find the stochastic representation for a solution. So if, for example, we take this here as a kernel, included in our equation, then we actually have a time fractional version of the heat equation. And then the mechanism is sort of always the same. So we choose K, then based on that, we get this function phi. In this case, it is in terms of the one parametric Mittag-Leffler function, which for appropriate beta is known to be completely monotone. So everything is fine here. And then since this K is also homogeneous, we actually only need one random variable, A beta, it is called here, which has such an appropriate Laplace transform. And then we see that we have this Feynman-Kac formula for a solution of our equation. And in this way, we could also take different kernels and then again just get the appropriate phi and then get the random variables AT, which we need for the stochastic representation. And then, of course, also we could, instead of taking just the Brownian motion and the Laplacian, we could take some other process. So if we stay with the same kernel, we could still choose as a process something different. So for example, we could choose the 2 gamma stable Levy process, which then as an infinitesimal generator would give us fractional Laplacian. So our equation would then turn into a time and space fractional version of the heat equation. And then again, our theorems would give us some stochastic representation of the solution. Okay, so with this, I think I have demonstrated a bit the use of those previous statements, although it was actually only the most easy example possible. Yeah, but this is it actually from me. Thank you for the attention. And then probably there will be some further comments or questions. Yeah.
So probably I will give a comment if there are no other remarks. So do you hear me?
Yes, we can hear you.
Yes. Yeah. Okay. So such type of Feynman-Kac formula are known in the case when our kernel belongs to a particular class of kernels which are of convolution type and are related to some subordinators. Then in this case, one can take this A of t, so without any homogeneity of the kernel, so just a kernel K, which is of convolution type and related to some subordinator. In this case, one can, such Feynman-Kac formula are known, and this A of t is exactly the inverse subordinator related to K. But we have, in our work, we have completely different approach, which allows us to construct such a Feynman-Kac formula for a much bigger class of kernels K. In particular, also kernels which are not of convolution type. In the example, you see the time fractional heat equation. This kernel is of convolution type, and the results are known in some sense. But you see, in our approach, instead of A of t being the inverse subordinator, which is a non-Markovian process, we have only just one bit variable, random variable A of b, and so we have, so to say, we have separated in our time change A of t, we have separated randomness and time dependence in sometimes nice way. So conditionally, everything is Markov. So that's all what I wanted to say.
Very interesting, thank you. And may I ask you about this fractional derivative heat equation, maybe 3 and 4? Does it relate to some physical model of super diffusion, I think, yeah?
Well,
Yes. Oh, Marie, you are the speaker.
Well, yes, I think in general, just taking these fractional derivatives and fractional Laplacian also is used in modeling anomalous diffusion. So probably if you choose a derivative with respect to time with some beta between 0 and 1 here, that would probably lead to a kind of subdiffusion. And then on the other hand, I think including the fractional Laplacian here, I would imagine that would lead to including jumps in your diffusion. So that would probably lead to some kind of
Levy flights, yeah.
Yeah, also that.
Okay, thank you. Maybe some other questions or comments, please. If there are no any other comments, then I have to say that now we will stop our session because the last speaker is not able to present her talk due to some personal reasons. So what I have to say, thanks every speaker today for interesting talks, and in a few days you will obtain some certificate about this conference, participation in this conference. I wish you success on on your mathematical way, and hope to see you again at our seminar. As already not student speaker, but arbitrary participant of the seminar. Thank you very much. And the last question to Georgi. Georgi, this is our last session, or we have something for next week?
For next time, I think Andrey Yurievich Pilipenko.
Oh, okay. So this is not the last session of our seminar. See you next week.
Okay, thank you. See you next week.
See you. Goodbye.
See you.
Thank you.
Bye.
Goodbye.
Bye.
Thank you. Bye.